Okay. I would recommend that you practice these problems from the practice sheet, which I've already given. So let us do something that is slightly different. Let us take this. Okay. So if head means 1 and tail means 2, then the coefficient of quadratic equation ax square plus bx plus c are chosen. The coefficients, it should be coefficients of the quadratic equation ax square plus bx plus c equal to 0 are chosen by tossing 3 fair coins. Find the probability that the roots of the equation are imaginary. So now what are the possibilities? A can take value 1 or 2. B can take the value 1 or 2. C also can take value 1 or 2. So the sample space, okay, it is a triplet basically, ABC. Okay, it can consist of, S, the sample space of, it consists of the ordered triads ABC. It can be 1, 1, 1, 1, 1, 2, so on. 1, 2, 1, 1, 2, 2. How many such combinations? N of S. A can take two values, either 1 or 2, that is heads or tails. B can take another 2 and C can take another 2. So we get 8. N of S is 8. There are 8 possibilities. Now find the probability that the roots of the equation are imaginary. So we have to show that the discriminant b square minus 4ac must be negative. For which values of a, b, c will this be negative? This is what we need to see. So let us fix. So for what cases we can get this? So let's put B, all right, or A, B, C, and the discriminant. If B is 1, if B is 1, we'll fix that first. Then A can be 1, and A and C can either be 1 or 2, because this is 1. 1 minus 4 times minimal of, if you multiply A and C, now minimum values is 1 and 1. So discriminant will be 1 square minus 4, which is negative. So this will be negative. So if B is 1, no matter what we choose, A and C, we'll get negative. So we'll get four options actually. If B is 1, A and C can be 1, 1 or 1, 2 or 2, 2 or 2, 1. So in all these cases, B square minus 4AC will be negative. Next, if B is 2, if B is 2 and A and C are 1, 1, then discriminant will be equal to 0. A is 1 and C is 1. Then discriminant will be equal to 0. If any one of them is equal to 2 or both of them are equal to 2, then the discriminant will be negative. 4 minus 4 AC. So 2 into 2, 8. So 4 minus 8 becomes minus 4. So it is negative. So the 8 cases, discriminant will be negative in 7 cases. Okay. So roots are imaginary. So roots are imaginary. So the possibility is, so if E is the event that the roots are imaginary, then n of E is 7. Therefore, the probability of the event E is n of E by n of S. So it is 7 upon 8. It is 7 upon 8. Okay. Is this clear?
Yes, sir.
Okay. Others you can practice. Now we'll move on to addition theorem. Now, addition theorem and related results. So the addition theorem. This is the basic addition theorem, and this is the generalization. Now, for two events, the addition theorem states like this. P of A union B is P of A plus P of B minus P of A minus A intersection B. Now, we can understand this by these Venn diagrams. So generally, the sample space is denoted by a box like this. So this is the sample space S. Now, let's say A is an event. So number of cases that are supportive of event A is marked with a region within the sample space. So this is the entire space, and a region within the sample space is considered to be event A. And let's say there is event B. So this is the event B. Now question is A union B. So A union B means the event that either A or B or either or both A and B occur. That means either A occurs or B occurs or both A and B occur. Okay. Either only A, only B, or both A and B occur. So now if you see that, that means at least, or we can say that, in other words, A union B means at least one of A or B will occur. This is what is the meaning of A union B. There are elements of A and elements of B. So A union B means at least one of A or B will occur. So now, so to do this, what we have to do is we have to go to sets and see what is the cardinal number of A union B. So A union B represents, I will draw this in two portions. So A union B refers to this region containing only A but not B is this region. Then it contains this region only B but not A. And this is both A and B. So the entire shaded portion taken is A union B. Okay, this is the shaded portion is A union B. So now A union B is N of A. N of A is this region. The total A. N of A. That means B is also included. Portions of B, wherever intersection. This is N of A. That means the event A, the simple events in favor of the event A. This is N of A. The next N of B. For N of B, you have this. Okay. This is N of A, this is N of B, this is N of A intersection B. So by logic, you can see I just want the shaded portion, either A or B or both. So I just want the entire shaded portion. How will I get? I take n of A. So I get this region of only A and A intersection B, n of A plus n of B. N of B is this shaded portion and this intersection. So in the process, see, we want to count all the shaded portion once. But what have we done? We have counted this combined portion A intersection B with A. And also we have included this region again in the count with B. So we have included it twice. We should have included it once. So we eliminate it once. So A union B is n of A plus n of B minus n of A intersection. Okay. Again I repeat. See, n of A union B is this full shaded portion. You take it one shaded portion. This shaded portion is n of A. I take n of A plus n of B minus n of A intersection B. Because n of A, I'm counting this intersection region once. N of B, I'm counting this intersection region twice, but I have to count it once. So I'm including it twice. So I have to exclude it once. So this is the principle of inclusion and exclusion. So, these are from sets. Now dividing by the total size of the sample space, you get n of A union B by n of S is equal to n of A by n of S plus n of B upon n of S minus n of A intersection B by n of S. So we have divided both sides by n of S. So left side gives us probability of either A or B occurring. This equal to P of A plus P of B minus P of A intersection B. So this is the result. P of A, P of B minus P of A intersection B. So this is the fundamental theorem. Now, if we go for 3, addition theorem for 3 events. So addition theorem for 3 events, A, B, C. So this is n of S, the size of the sample space. Then we have, say this is A, that I'll change colors. This is B. And this is C. So now addition theorem for 3 events states like this. Probability of A union B union C is probability of A plus probability of B minus plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of C intersection A plus probability of A intersection B intersection C. So how did we do this? So now A union B union C is the entire region taken once. It is at least one of A, B, and C. So we can write that A union B union C is the occurrence of at least one of A, B, or C. So this is the shaded portion. Now this is the shaded portion we want. So now we'll make colors. Just see this. Now this region is A intersection B. This region is A intersection B. Now this region is B intersection C. B is overlapping with C. And then C intersection A. A is overlapping with C. Okay. So now I want to get the entire shaded portion. Now this is equal to P of A once. So P of A means all common regions you're counting once. P of B, then this two counting regions you're counting twice. And then P of C, you're counting this one is counting this as the thrice. So when you do P of A, you're counting this whole region plus P of B, you're counting the whole region plus P of C. So you're counting this whole regions. Now, when we took P of A plus P of B, this plus this, so this whole region is included twice. When we do P of A plus P of B, so minus P of A intersection B. Then between B and C, it will be P of B intersection C minus twice. We have chosen, so once we eliminate. And then C intersection A, again it was chosen along with A, along with C, we have to choose it once. So P of C intersection A plus. So now this middle portion here, this particular middle portion here is an interesting portion. Now this portion is included with A, included with B, included with C, removed from A intersection B, removed from B intersection C, and removed from C intersection A. So in the process, we have included this region thrice and we have excluded it thrice. So, but we want to include that region. So one more is added, P of A intersection B intersection C. Okay. So that's how we get this. So this is what is addition theorem, and this is sufficient for most general. It is n factorial. So this is the most general form of this result. Generalizing to n events. It is sigma summation of probabilities of the single event, P of A plus P of B plus P of C. So it is A1, A2, A3 here up to AN, minus taking combination of two, A1 and A2. All such combinations plus combinations of 3, A1, A2, A3, minus combinations of 4, plus combinations of 5, minus combinations of 6, plus combinations of 7. Like that, we can go on calculating and we'll get a idealistic, sorry. So when we do that by this overlap, by this, see, this is inclusion, exclusion, and again inclusion. So this is called as the, we are using this as principle of inclusion and exclusion. So we extend that to that n cases also. Principle of inclusion and exclusion, this one. So if you remember this, you can do it for any number of events. First, include all the single events, minus exclude once all the events that occur simultaneously, this and this, and then add the events that occur thrice together, the event that occurs 3 together, all such cases, plus no, next is minus the probabilities of 4 events occurring together. Like that you do, you get the result. This is the addition theorem of probability, and we have some very useful results with the addition theorem. Very useful theorems, we will just see. Now, what if there's the extension of the addition theorem? If A and B are mutually exclusive events, when we say exclusive events, see from this diagram, this is the sample space, and we have event 1 and we have event 2. So this is event A, this is event B. Okay. Now event A and event B are mutually exclusive, means if one occurs, other does not occur. Now, if they are not mutually exclusive, then there will be an overlap like this. So this region indicates that both A and B occur simultaneously. This region indicates that both A, B, and C, all 3 occur simultaneously. This region here indicates that A and C occur simultaneously. This region in green here indicates that B and C will occur simultaneously. However, exclusive event means when one occurs, other cannot occur. So such cases are depicted like this. This is A, this is B. So they're mutually exclusive. So for mutually exclusive events, A intersection B is phi, which implies probability of A intersection B is phi, probability of 0, probability of null set, which is 0. So what we get is P of A union P of B is P of A plus P of B minus P of A intersection B. No. So this becomes 0 here because they are mutually exclusive. When they are mutually exclusive, the intersection is 0. So you get this. So from here we get P of A union B is P of A plus P of B. This is for mutually exclusive events. They're mutually exclusive. Now generalizing this to n events, if A1 union A2 union A3 union so on up to AN, we take the probability of this any one of them to occur. At least one of A1, A2, A3 up to AN. Probability of at least one of these events to occur is, because all are mutually exclusive events. A1, A2, A3, AN. If all are mutually exclusive events, we'll get like this. A1, A2, A3, A4, A5, A6, A7, like that. There is no overlap between any of these mutually exclusive events. If one event occurs, the other cannot occur. If A1 occurs, other up to A2 to A8 cannot occur. So these are mutually exclusive events. So this gives that P of A1 union A2 union A3 union AN is equal to P of A1 plus P of A2 plus P of A3 up to P of AN. So this is the extension of addition theorem for mutually exclusive events. Okay. Next, proceed further. This is a very important the result which we will use in Bayes' theorem and compound probability. Very, very important to understand. So if event A must result in one of the mutually exclusive events, A1, A2, A3, AN, then probability of A is A intersection A1 plus probability of A intersection A2 plus probability of A intersection A3, so on, plus probability of A intersection AN. So how does this happen? Example I'll take. Let's say we have 3 bags. Okay. This is bag A1. Bag A2. Bag A3. Now this contains different kinds of balls, different colored balls. Okay. Say you have yellow. You have not, I'll not choose. You have red. or maroon. And then we have green. Each one has its own combinations of balls. Okay. Blue, red. I'm giving this example so that you remember this thoroughly. I'm taking time because once you get this, that's it. So there are different bags and there are different colored balls in each bag. So now from these three bags, I randomly choose one ball at random. Okay, A is an event. A is the event that I choose a red ball from any one of the three bags. So A is the event of choosing a red ball from any of the three bags. Now, the issue here is if I choose A, then automatically it implies that I will choose one of the bags. Correct? If I have to choose a red ball, inherently means I have to choose a bag also. So that is the meaning of saying that event A must result in one of the mutually exclusive events. See, if I choose bag A, it is not that I can choose bag A2 and A3 simultaneously. No. If I choose bag A, that it excludes choosing bag A2 and bag A3. So these are mutually exclusive events. Choosing the bag, choosing one bag A1 or A2 or A3 are mutually exclusive. These are mutually exclusive events, correct? So if I have to choose a red ball, it necessarily means choosing a red ball. This is event A. Necessarily includes choosing a bag A1 or A2 or A3. So therefore we say P of A, choosing a red ball, is in this case choosing probability of choosing the bag A1 and a red ball from bag A1, probability of choosing bag A2 and a red ball from bag A2, plus probability of choosing bag A3 and a red ball from bag A3. Okay. Probability of A1 intersection A plus probability of A2 intersection A, probability of A3 intersection A. So probability of choosing a red ball is probability of choosing the bag A1 and a red ball from bag A1, probability of choosing bag A2 and a red ball from bag A2, and probability of choosing bag A3 and a red ball from bag A3. Is this clear? This is a very important result, not immediately obvious, but in problems on conditional probability and Bayes theorem, we will use this theorem very, very much. So three theorems we discussed. One is the basic addition theorem. Okay, for two events and for 3 events, and for the general n events, it is given here. Next, then for mutually exclusive events, all intersection terms vanish. So without the intersection terms, we get the result. And this result, if an event A must result in one of the mutually exclusive events, then we get P of A is this expression. I took time to explain this. Now, let us look at some more useful results. Very, very important results, and so many bits and objective questions come around this. First one is an extremely important inequality. If A and B are two events in S, then P of A intersection B is less than or equal to P of A or P of B, and each of them is less than or equal to P of A union B, and this is less than P of A plus P of B. Very, very important result. We will explain this with the diagram. P of A intersection B less than or equal to P of A or P of B. Which is less than or equal to P of A union B, which is less than or equal to P of A plus P of B. So let's look at this. So P of A intersection B is this. So P of A intersection B, this region, the intersection region, will naturally be less than P of A and less than P of B. So P of A intersection B is less than P of A, or P of A intersection B is less than P of B. So next, now P of A is this region. Okay, just this region enclosed within this light yellow line. But P of A union B is this entire region. Now, naturally, P of A or P of B will be less than this. These two will be equal only when they overlap. A or B completely overlap each other. So only then this will be equal. Otherwise, or when one of them is 0. P of A or P of B is 0. Anyway, in most cases, this is less than P of A union B. And now P of A union B will be less than P of A plus P of B. P of A plus P of B will include this region twice. Intersection region, this one, it will include twice. This is the intersection region. P of A plus P of B. So this region is included twice. So therefore, we get P of A union B is less than P of A plus P of B. And in fact, so this, if we just draw this Venn diagram, it will be very, very clear. All these inequalities are self-obvious. If we don't look from this point of view, it becomes difficult. Is this clear? Anybody has any questions here? You can raise hands if you have doubts. If everything is clear, then we'll proceed. Okay, no one has doubts. So let's proceed. The second result here is just the extension of this result. P of A union B is less than P of A plus P of B. So P of A1 union A2 union so on union AN will be less than P of A1 plus P of A2 plus P of A3 so on plus P of AN. On the other hand, now the intersection, let us do this for 2, then we can understand for all. This is P of A1 intersection A2 intersection A3 so on intersection AN is greater than or equal to 1 minus P of A1 bar, P of minus P of A2 bar minus P of A3 bar minus P of AN bar. Okay, how this works? For 2, we can show P of A1 intersection A2, or so your P of, so what we have to show here is P of A intersection B is less than or equal to, oh, sorry, greater than or equal to 1 minus P of A bar minus P of B bar. So 2 steps to prove this. First one, P of A intersection B is this region. Now this, yeah. Now P of A intersection B this is equal to 1 okay, this is like P of A minus P of P of A but not B. Okay, there are many other ways to do it. Okay, anyway, we will show this way. Now P of A intersection B yeah. Now P of A bar is this entire region. plus P of B bar. B bar is this entire region again. So all except for A. So P of A bar, P of A bar includes B here. Okay. So P of A is equal to 1 minus P of A bar, or P of A bar is equal to 1 minus P of A. Now P of B bar is also 1 minus P of B. So now P of A bar plus P of B bar is 2 minus P of A minus P of B. Multiply this whole thing with a minus sign. So minus P of A bar minus P of B bar is minus 2 plus P of A plus P of B. Okay. Next, I add 1 to it. So 1 minus P of A bar minus P of B bar is P of A plus P of B minus 1. Okay. So this is equal to P of A plus P of B minus 1. So this part we can easily prove. Okay. So from here, what we get is, take this to this side. 1 is less than or equal to, greater than or equal to P of A plus P of B minus P of A intersection B. So which means that 1 is less than P of A union B, which is true. P of A union B, by definition, any probability will be less than or equal to 1. So which means go reverse. P of A plus P of B minus P of A intersection B will be less than or equal to 1. Take this to the other side and bring minus this side. So P of A intersection B is greater than minus 1 plus P of A plus P of B, which means P of A intersection B is greater than, we can write this as 1 minus P of A bar, 1 minus P of B bar. So we get this result. So P of A intersection B is greater than 1 minus P of A bar minus P of B bar. This part, okay, I will do this exclusively. Now we'll do a lot of problems on this. Few, not many, but we need to understand this. So how do we mean which probability means what? So verbally, if we say that probability of both A and B occurring, both A and B occurring, it means P of A intersection B. Then probability of at least one of A and B occurring, it means P of A union B, right? For two events. Probability of exactly one of A and B occurring, exactly one of A and B occurring. How will that be? A occurs but not B, plus B occurs but not A, B. So A but not B means this. This region A, which does not include B. And then B but not A is this region. A but not B, B but not B. So exactly one of A or B occurs. If this event falls within this region, it means only A has occurred. If it falls in this region, it means only B has occurred. So this is the region. When you say exactly one of A or B occurs, it means this. So this is showing probability of A but not B. A intersection B bar, A and not B. So this is nothing but probability of A. See this? Probability of A, this region, minus this region, minus probability of A intersection B. Similarly, probability of not A but only B. Okay, probability of B but not A. This is this. Probability of B intersection A bar or A bar intersection B. It is probability of B minus probability of A intersection B. So when we add this, when we add these two, adding these two, we get this result. P of A intersection B bar plus P of B intersection A bar is P of A minus P of A intersection B plus P of B minus P of A intersection B, which is P of A plus P of B minus 2 P of A intersection B. Now take one of them minus P of A intersection B and add with P of A plus P of B, you get P of A union B. So you get, see here, A union B total minus A intersection B. That's all. Total A union B minus this gives exactly one of A or B occurring. So this result is an important result. P of A intersection B bar plus P of B intersection A bar is P of A union B minus P of A intersection. Okay. So these are some results, and then the same thing extended for 3 events. So this terminology is important, and when we deal with problems, we should know these terminology. Now, if A and B are 3 events, then probability of all of them occurring is P of A intersection B intersection C. At least one of them occurring is A union B union C. Just a second. So next, look at this. Probability of occurring of exactly one of ABC. This is little more involved. So you can see probability of A, but not B, not C. So if we draw this Venn diagram, A, B, C. Now A, B, C. Probability of A but not B, not C means these regions excluded. So then probability of B but not A and C means this region. Probability of C but not A and B means this region. So occurring of exactly one. So this green portion is what this means. Probability of exactly one of the events occurring. So you can write this as A union B union C minus P of A intersection B minus P of B intersection C minus P of C intersection A. However, in the process, see, we have to subtract this whole region once from A union B union C. This whole black gray shaded region has to be omitted once. Now what is happening? I take P of A intersection, sorry, this is same as P of A union B union C minus P of A intersection B intersection C. So I have excluded this region, minus P of A intersection B. I have excluded here. Then I exclude this region, P of C intersection B intersection C. Okay. Next, I include P of C intersection A. Exclude. I exclude this. What happens in the process? This inner region, this particular region, I have excluded along with A intersection B. I have excluded along with B intersection C. I have excluded along with C intersection A. How many times I have to exclude? Once. But how many times have I excluded? Thrice. So therefore, I have to add that twice. So this is what is this. So I have added that twice. Okay. And then apply this P of A union B union C formula, we get this. And simplify, you get this. But this step is the crucial, what I've explained. The next step is just applying the basic addition theorem of probability and using. Now probability of at least two of A and B occurring. At least two of A and B occurring means either two should occur or three should occur. So this is this region, this whole pencil region here, what we showed earlier. So this region shows that at least A or B occurs here, at least B or C occurs here, at least C or A occurs here, and here all three A, B, C occur. So when you say at least two of A and B should occur, A, B or C should occur, it means this inner, this all region bounded by red color. So it is A intersection B but not C plus B intersection C but not A plus C intersection A plus but not B plus A intersection B intersection C. So that turns out to be P of A intersection B plus P of B intersection C plus P of C intersection A. Now I've included the inner region thrice. I have to subtract it twice. So instead of counting it once, I've counted thrice. So I have to reduce it by 2. So I get this. Now suppose the question is exactly 2 of A intersection B intersection C. Now when you say exactly 2 of A intersection B intersection C, it will be this region. This is A, this is B, this is C. Now exactly 2 of, so this is the region where A and B occur. This is the region where B and C occurs. And this is the region where C and A occurs. So exactly 2 means this is the area we see like this. So probability of finding this is probability of A intersection B, this whole region, plus probability of B intersection C, plus probability of C intersection A, minus probability of A intersection B intersection 3. I have counted it thrice, so I have to remove it thrice. So that's how I get this. Okay. So this was addition theorem. Now let's do some problems. On the addition theorem. Simple ones first. Okay. Naveen, I'll get back to you. I think you're asking this, right?
Yes, sir.
This one. At least two of A, B, C occur. This is what you're asking?
Yes, sir.
So it means at least two of them occur means either two of them occur or three of them occur. So it is A and B occurs, but not C. B and C occurs, but not A. C and A occurs, but not B. And all three can occur simultaneously. So this first part is A intersection B, but not C, is this region. I will shade it with this red color. A and B, but not C. So C is here, no? So I exclude C. Then B and C, but not A. So I this do this here. No, I will not use yellow. I will use blue here. B and C, but not A. So this region. Okay. And then one more color I'll use different from these two. Okay, I'll use green. I've already used. Okay, gray only. A and C, but not B. So this is this region, A and C, but not B. Okay. And A, B, and C, all three occurring simultaneously. So at least one of the two occurring means either two occurs or three occurs. So I want this region. For this region, what I do is I take A union, no, I take P of A intersection B. So that is what is. Then I take P of B intersection C. Then I take P of C intersection A. So now what has happened, this inner yellow portion, I should be counting once, but I have counted it three times along with A intersection B, along with B intersection C, and along with C intersection A. This region has been counted thrice, but I should have been counting it only once. So I will have to subtract this region twice. Therefore, I get this minus 2 times P of A intersection B intersection C. Is it clear? Okay, good. So if it is exactly two of them occurring, then we have to subtract 3 times of this. Okay. So now let us do this. Now let us do problems on addition theorem. For a single post, 3 persons A, B, C appear in the interview. Probability of A being selected is twice that of B, and probability of being selected is thrice that of C. What are the individual probabilities of A, B, and C? Here, inherent assumption in the question, if you observe carefully, inherent assumption is one of the 3 persons has to be selected. That means it's an exhaustive event. Okay, either A will be selected or B will be selected or C will be selected. And one more thing, anybody? What else can you say about this? For a single post, 3 persons appear in the interview. First, write the events. Event A is the event that person A is selected. B is the event that person B is selected. C is the event that person C is selected. Okay. What are the individual probabilities? What is P of A union B union C? What is the probability that at least one of them will be selected? Anybody?
1.
Very good. Good. This is exhaustive. So probability that at least one of them is selected. Is 1, because that is assumed in the question. It is not mentioned, but indirectly it is assumed that way. Now, are these mutually exclusive or not mutually exclusive? Anybody? How do you understand mutually exclusive? If A is selected, what happens to B and C? They can also be selected?
No, they can't be selected.
Yes. So if A is selected, we exclude selection of B and C. If B is selected, we exclude selection of A and C. If C is selected, we exclude the selection of A and B. So which means that these are mutually exclusive events. So therefore, P of A union B union C will be P of A plus P of B plus P of C. The intersection will not happen. A comma B, since A, B and C are mutually exclusive. So it's an oral question, but we have to understand these concepts. Okay, they are mutually exclusive events. Now, probability of A being selected is twice that of B. So P of A now, P of A is 2 times P of B. And probability of B being selected is thrice that of C. And probability of B is 3 times P of C. So therefore, P of A will be 2 times P of B is equal to 2 into 3 times P of C is equal to 6 times P of C. So let us do this calculation now. So let P of C be equal to K. Then P of B will be equal to 3P of C, which is 3K, and P of A is 6p of c, which is equal to 6k. Now, since from here, because they are mutually exclusive, since p of a plus p of b plus p of c is equal to 1, we get 6k plus 3k plus k is equal to 1. So we get 10k is equal to 1, k is 1 over 10. Thus, p of a is 6 over 10, p of b is 3k, which is 3 over 10, and p of c is 1 over 10. Okay, so this is the result. 6 over 10 or 3 by 5, 3 by 10, 1 by 10. Clear how we solved? There are two things which are silently said in this problem. One is that definitely one of them will be selected, and that these events are exclusive, that it is up to us to judge whether they're exclusive or not. All right, clear? We'll proceed to the next. Is on inequalities. Okay, I leave this question to you. I'll give some time, 5 minutes. Let's see the answer. I'll give you 3 minutes. Okay, good. I got one correct answer. Problem is simple. Yeah, it is. Two candidates are seeking admissions. Now, probability of A union B means either A or B getting selected. This has to be less than or equal to 1. Okay. Because it cannot be, no probability can be greater than 1. So, probability that A is A, okay. P of A union B is P of A plus P of B minus P of A intersection B. Now, given that probability this is equal to 0.5 and this is at most 0.3. That means this is less than or equal to 0.3. So let us begin from here. P of A intersection B is less than or equal to 0.3. So P of minus P of A intersection B minus P of A intersection B should be, if you multiply with a minus sign, this will be greater than or equal to minus 0.3. Actually, it's directly, you can say this. See, directly here, this is 0.5. Even if this is 0, even if this is 0, okay, there's no subtraction. 0.5 plus 0.9 will be 1.4. So it is impossible for P of B to be 0.9. So in any case, let us check this. So P of A intersection P of B is minus 0.3. Now you add P of A plus P of A plus P of B to it. So this is greater than or equal to, this is greater than or equal to P of A plus P of B minus 0.3. Now this is greater than or equal to P of A is 0.5 plus P of B minus 0.3. Left hand side is what? P of A union B. So P of A union B is greater than or equal to 0.2. Now P of A union B is greater than 0.2 plus point B, but this itself is less than 1, right? So which means 0.2 plus P of B should be less than or equal to 1, which means P of B should be less than or equal to 1 minus 0.2. So P of B must be less than or equal to 0.8. So it should be less than or equal to 0.8, then only it is possible. It cannot be 0.9. So of course here I did a full valuation to show if the question is whether it can take 0.9, it is no. Straight away seeing this step only. You don't have to go much further. So even if it is 0.3, it is 0.2. So P of B maximum value it can take is 0.8. All right. Like that we can see that. So P of B should be less than or equal to 0.8. Clear? Next. One more. 3 events. This is important. We'll try this. If A, B, C are 3 events such that P of A is 0.3, P of B is 0.4, P of C is 0.8, P of A intersection B is 0.08, A intersection C is 0.28, A intersection B intersection C is 0.09. If union is greater than 0.75, find the interval in which P of B intersection C lies. Please do this. This I'll give 2 minutes time only. Okay. Why none of you are able to do this? Very simple. P of A union B union C is greater than 0.75, but it has to be less than 1. Correct. So this implies P of A union B union C is P of A plus P of B plus P of C minus P of A intersection B minus P of B intersection C minus P of C intersection A plus P of A intersection B intersection C. So this should lie between 0.75 and 1. So this, now you keep adding values, 0.3 plus 0.4 plus 0.8 minus A intersection B is 0.08. A intersection C, this we have to find B intersection C. C intersection A is 0.28 plus 0.09. So let's calculate. 3 plus 4, 0.7 plus 0.8 is 1.5. So 1.5 plus 0.09 is 1.59 addition. And then subtraction minus 0.28 plus 0.08. So that is 36. So we get 1.323. 1.23. 1.23. So now subtract 1.23 on both sides. So if it was 1.25, so minus 1.23 and 0.75. So it will be 48 minus 0.48. No, minus 1.23 we are doing. So I've done minus 1.23 on both sides. Now I multiply with minus sign. So when I multiply with minus sign, the inequality reverses. So I'll get 0.23 to 0.48. This is the answer. Okay. Before we go into okay, the other ones you try. This is a simple one. You can just try this. Answers are here. You please try today. Tomorrow we will do multiplication theorem. We still another 15 minutes. I think I'll do this. I'll ask you to do this. Anyway, we started late. I forgot. So please do all these five and give answers quickly. Okay, many of you have done and correctly. So directly it is given. So first one is P of A union B is P of A plus P of B minus P of A intersection B. So this is 0.4 plus 0.3 minus 0.15. This is 0.55. So 0.7 minus 0.15, 0.55. Second, P of A bar intersection B. This is not A, but B. So this is B, but not A. So P of B minus P of A intersection B. So this will be 0.3 minus 0.15, which is 0.15. Then P of A, but and not B. That means P of A minus P of A intersection B. So only A. So it is 0.4 minus 0.15, which is 0.25. Fourth one, P of A bar intersection P of B bar. Yeah, this one we have not discussed, but let us see who would have done right. I'll give the answer. This is A, this is B, A bar. I will mark with, say, orange. This is A bar. A, not A. This is A bar. Intersection not B. Now, not B, that which is not B, I will mark with, so all this is not B. I'll mark with green. Okay. So intersection of these two means intersection of the orange lines and the green lines. That is, if you see, observe carefully the intersection, it is nothing but 1 minus A union B. So actually, this is a very important result actually. A union B whole bar is 1 minus is P of A bar intersection P of B bar. The next one is the reverse. So this is a very important result. So this is 1 minus 0.55, which is 0.45. And the last one, similarly, P of A bar union B bar. Union means A bar, B bar, and or both A bar and B bar. So A bar is all green lines, B bar is no, A bar is all orange lines, B bar is all green lines, and intersection is outside. Now, when you say union, it is either A or B. So either green lines or orange lines or both. Okay. So that is nothing but total minus P of A intersection B. So this is 1 minus P of A intersection B bar. So this also is an important result. P of A intersection B whole bar. is P of A bar union P of B bar. These two are very important results in this addition theorem, logically. So this is 1 minus intersection is 0.15. So it is 0.85. and 0.45, correct. So please check your answers and the solution here. So, okay, today we'll stop here. Tomorrow's class at 4, unless there is any change. I intend to start sharp at 4. Tomorrow will be multiplication theorem, independent events, and multiplication theorem, and the conditional probability. So Bayes theorem also included. Tomorrow we'll cover that. Thank you.
Thank you, sir.
Yeah.